direction. And the shear stress is equal to TR over J. And I'm only drawing at the surface because the shear stress is maximum, right? Tau max is maximum, is located at where? Tau max. Okay. So the next thing I want you all to see now is we are going to focus on element. Okay, we're going to focus on elements B and element D. Okay. Note, later on you'll see this, the shear flow Q at elements A and C are equal to what? Are equal to 0. Okay. So now let's focus on element B. Okay. So if we look at element B, right, and the shear stress at element B will be equal to what? TR over J. Okay. And then the next one, we know that we will have a By over IZZ QZ over T. Okay. Now we are going to assume, okay, we're going to assume that when the shear stress is coming down, it is what? Positive. I repeat again, when the shear stress is coming down, it is what? It is positive. So I want you to focus on element B. Okay, I want you to focus on element B. If you look at the shear flow over here, Q is going which way? Downwards. Yes or no? And then if you look at element B, due to TR over J, the shear stress is also what? Going down. When this is the case, you add the both of them. You decide whether is it positive or negative. Okay, there's no rule that up is positive, down is what? Negative. If you decide to pick down as positive, everything coming down is positive. Why is it? It does not matter. Anyone? This is like a Mohs circle question. Why it does not matter? Oh, this is a good question for tomorrow. Why it does not matter whether is it positive shear or negative shear? Which is better, positive or negative shear? Anyone? Does not matter. Are we clear? It does not matter whether positive shear is better or what? Negative shear is better. It's not like normal stress where positive normal stress sometimes is no good for what? Brittle material, but negative normal stress is good for what? Brittle material. Are we clear? Okay, so it does not matter at all. So the next thing we define, if we look at now, is element A or element D. If we look at element D, again, positive is coming down for shear stress at element D. This one, we have TR over J. You have V Y over IZZ QZ over T. Okay. Now, I want you to pay your attention to the shear flow. Now the shear flow is coming down. When the shear flow is coming down, we declare this is going what? Positive. Yes or no? And then if you look at this one, you look at due to the torque. Now you see due to the torque, this direction is going what direction? It's going where? Upwards. So when that's the case, you put over here, this is the what? Negative. So you can see that element B has the highest what? as the highest shear stress. Are we clear? Okay. So what are we trying to calculate over here? Okay, what are we trying to calculate over here? So remember, again, using the assumption of our what? Let's say we have a beam again. And the beam, right? Again, we have our P. And over here, we have our point A, we have our point B, and this is our P/2, assuming both of them have equal distance of length where the force is applied. This is L/2, and this is L/2. Okay. So now, if we were to label this at point C, right? At point C, where will failure occur? Failure occur at where? Anyone? Failure will occur at point C. Failure will occur. And we know failure will occur at point C. Why? Because point C, we have what? At point C, we have V max or Vy max is equal to P/2. Okay, so I'll draw our transformation again. This is X, this is Y, and this is our rotation about Z. Okay. And then we also know that moment in the Z direction is maximum, and this is equal to what? PL/2. Okay. Now, we are now going to make, or we are going to now draw the cross section. So assuming that this is our cross section. Okay, again, this is our cross section. So the first thing that we know, if we apply, or if we were to apply a formula, right, that our stress, our normal stress X is equal to mz over izz multiplied by y. Okay, so now I'm sketching our, so this is our y, this is our z, and this is our rotation in x. So from here, when we sketch our normal stress out, okay, right? When we stretch our normal stress out, so we know based on moment vector, this is our moment in our Z, and this is in compression, and this will be in what? Tensile. So when we sketch this out, it looks like this. Okay, when we sketch this out, it looks like this. So over here at the top is in compression, and the tail end is in what? Is in tension. Okay. Now, the next formula that we are going to sketch now, this will be our shear stress, and this is our Y. Okay, so the shear stress that we're going to plot, so the intersecting plane is in the X, direction of the shear stress is Y, so this will be equal to Vy over Izz Qz over T. So how does this look like now? So when you sketch out the shear flow or the shear stress, the magnitude now looks like this. So this is for a rectangular cross-sectional area. Okay. Can someone make a comment on this graph, please? What can you see? What can you see? I want you to focus on the centroid. At the centroid, what is the normal stress? Anyone? At the centroid, the normal stress is equal to what? 0. The shear stress at the centroid is equal to what? Are we clear? The trend is different now. Okay. We know that due to bending moment, stress X is equal to 0 at the where? Centroid. And we also know now what we observe is at the centroid, the shearing stress is at its what? Maximum. So now, if we were to sketch this in 3D now, okay? So again, this is our X, this is our Y, and this is our Z. Okay? And then we have a load P acting on our center, and we have two reaction over here. Okay? Now, question for you all. How is this surface going to fracture? Where is it going to break? Anyone? Is it going to break which plane? Is it going to break on the what? Is it going to break on the YZ plane? Is it going to fracture on the XZ plane? Or is it going to fracture on the XY plane? Where will fracture occur? Are you okay? You are awfully quiet today. It's like the silence before the storm. Are you okay? Okay? No? Don't be too stressed, okay? Question 1 for term test 2 is what? 2D mole circle. Question 2 is what? 3D mole circle. Question 4 is what? No, question 4. Question 3 is what? Combine what? Loading. All of them is going to be from where? From your homework and all from the lecture notes. Are we clear? Okay, stop panicking. Are we clear? Okay. So where fracture will occur? Right? We know fracture will occur on this surface. Right? We know that this is the fracture what? Plane. So that is why when we put our element here, right? We put our element. Okay, so this is our what? This is our element. So when we have our element, right? So when we put our element, what we see, and this is in 3D, by the way, what we see is we have an element over here. We have our stress Y, and then we have our shear going this way. Okay, and this is shear X, Y. Okay, Why is it XY? Because the plane intersects the what? Remember, we did this in Mohs circle. The plane intersect on the what? On the, so this is our plane. The plane will intersect the x-axis, and the shear flow or the shear stress or the shear flow is in this direction. So our shear stress is in this direction. So this is our shear stress or shear flow direction. Are we clear? Okay. Now, like before, the shear can occur in two different planes. So just to tell you what's going to happen tomorrow. In tomorrow's term test,